Have you ever wondered whether energy projects deep underground can trigger earthquakes? When we produce oil and gas, inject CO2 for carbon storage, or store hydrogen underground, we are not only moving fluids. We are changing pressure, changing stress, and sometimes disturbing faults that have been quiet for a very long time. In this video, I will explain this in a very simple way, using dynamic simulations and visual examples. No advanced mathematics is needed. By the end, you will understand why induced earthquakes happen, why pressure is so important, and how engineers can reduce the risk. Welcome back to the channel. Today we are going to answer a very important question. Can underground energy projects trigger earthquakes? This question is important for three major subsurface technologies. First, hydrocarbon production, where oil and gas are removed from the reservoir. Second, carbon capture and storage, or CCS, where CO2 is injected underground. Third, underground hydrogen storage, where hydrogen is injected and withdrawn repeatedly to support future clean energy systems. The key idea is simple. Underground energy operations change pressure. Pressure changes stress, and stress can change the stability of faults. So, let us go underground and see what really happens. First, let us understand why this topic matters. Induced earthquakes are not only a scientific topic, they are also a public safety question. People often ask, if we inject CO2 underground, can it cause an earthquake? If we produce oil and gas, can it make the ground unstable? If we store hydrogen underground, can repeated pressure cycling disturb faults? These are very reasonable questions. The good news is that engineers can study this risk before operation. We can simulate pressure, identify faults, monitor small seismic events, and design safer injection or production strategies. In this video, I want to make the mechanism easy to understand. We will focus on the underground story: pressure, stress, fault slip, and risk control. Induced earthquakes are not only a scientific topic, they are also a public safety question. People often ask, if we inject CO2 underground, can it cause an earthquake? If we produce oil and gas, can it make the ground unstable? If we store hydrogen underground, can repeated pressure cycling disturb faults? These are very reasonable questions. The good news is that engineers can study this risk before operation. We can simulate pressure, identify faults, monitor small seismic events, and design safer injection or production strategies. In this video, I want to make the mechanism easy to understand. We will focus on the underground story: pressure, stress, fault slip, and risk control. Before we talk about earthquakes, we need to understand what changes underground. A reservoir is not an empty cave. It is a rock formation with tiny pore spaces. These pores contain fluids such as water, oil, gas, CO2, or hydrogen. When we inject fluid, the pore pressure increases. When we produce fluid, the pore pressure decreases. These pressure changes may look invisible from the surface, but underground, they can influence the forces acting on faults. Let us start with the core idea. The core idea is very simple. Production removes fluid from the reservoir. This can reduce pressure and cause the rock to compact. Injection adds fluid to the reservoir. This can increase pressure and push the pressure signal outward. Hydrogen storage is different because it involves repeated injection and withdrawal. Pressure goes up, then down, then up again. So the reservoir is not static. It is constantly responding to our operations. For induced earthquakes, the most important question is not only, where is the fluid? The more important question is, where does the pressure change go? Now let us define induced earthquake in a simple way. An induced earthquake is a fault slip that is caused or promoted by human activity. This does not mean that humans create a new fault from nothing. In most cases, the fault already exists underground. The fault may be stable, or it may already be close to failure. Then human activity changes pressure or stress near that fault. If the change is strong enough, the fault can slip. That slip releases energy, and we may measure it as a small earthquake. So, induced seismicity is usually a combination of natural fault conditions and human-driven pressure or stress changes. But not every fault is dangerous. It is important to understand that not all faults are dangerous. Some faults are stable. Even if pressure changes nearby, they may not slip. Other faults are critically stressed. This means they are already close to slipping under the natural underground stress field. For these faults, Even a relatively small pressure or stress change can become important. This is why geological characterization is so important. We need to know where the faults are, how they are oriented, and whether they are close to failure. The next slide shows one of the most important ideas in this entire video. This is one of the most important messages for non-specialists. The fluid plume and the pressure footprint are not the same thing. Let us make effective stress very simple. Imagine a fault as two rock surfaces pressed together. The normal stress acts like a grip holding the fault in place. Pore pressure acts in the opposite direction. When pore pressure increases, it reduces the effective grip on the fault. So, higher pore pressure can make it easier for a fault to slip. This does not automatically mean an earthquake will happen, but it can reduce the safety margin if the fault is already close to failure. The failure concept can be explained in one line. A fault slips when the driving force becomes larger than the resistance. The driving force is shear stress. It tries to slide the fault. The resistance comes from normal stress and friction. It tries to hold the fault together. When pore pressure increases, the resistance can decrease. When production causes compaction, the stress around the fault can also change. So, both injection and production can influence fault stability, but through different pressure and stress pathways. Now let us look at the first real application, hydrocarbon production. Hydrocarbon production means removing oil and gas from underground reservoirs. Many people think only injection can trigger earthquakes because injection increases pressure. But production can also influence seismicity. When fluids are removed, reservoir pressure declines. The rock may compact. Surrounding layers may deform. Stress can be transferred to faults. So, even pressure decline can create a mechanical response underground. Let us watch the production story. In this visual, we start with a reservoir before production. Oil and gas are produced through the well. As fluids leave the reservoir, pressure drops. When pressure drops, the reservoir loses some internal support. The rock frame may compact slightly. This compaction can change the stress field around nearby faults. If a fault is already close to slip, this stress redistribution may become a trigger. The important message is this: production does not simply remove fluid. It changes the mechanical balance underground. Let us look more closely at why depletion can trigger slip. During depletion, the reservoir pressure decreases. The reservoir can compact because the rock grains carry more load. This compaction can bend or deform surrounding rock layers. If a fault cuts through or lies near the reservoir, the stress change may concentrate along the fault. The fault may experience a change in shear stress or normal stress. If the fault is close to failure, this can promote slip. So, depletion-induced seismicity is not caused by high pressure. It is caused by stress redistribution due to pressure decline and compaction. This leads to a common misunderstanding. A common misunderstanding is, lower pressure always means lower seismic risk. That is not always true. Lower pressure may reduce hydraulic pressure, but it can also increase compaction and change the stress around faults. This is why we should not think only in terms of pressure increase or pressure decrease. We must think in terms of pressure change, stress change, and fault stability. For underground energy systems, the safest operation is not just maximum production or maximum injection. It is controlled operation based on monitoring and simulation. Now let us move from hydrocarbon production to CCS. CCS means carbon capture and storage. The goal is to capture CO2 from industrial sources and inject it deep underground into suitable geological formations. This is important for climate mitigation, but safe storage requires careful pressure management. Why? Because CO2 injection increases reservoir pressure. If that pressure spreads toward a fault, the fault stability may change. The next slide shows the most important CCS concept. This is the key CCS idea. The blue region represents the CO2 plume. This is where the injected CO2 is located. The orange region represents the pressure footprint. Notice that it is much wider than the plume. This means the CO2 itself may still be far away from a fault, but the pressure signal may already reach that fault. For safe CCS, we must evaluate both the plume and the pressure footprint. A beautiful plume map is not enough. We need to know whether pressure is moving towards sensitive faults, caprock, or other wells. So what makes CCS different from normal injection? CCS projects may inject large volumes of CO2 for many years. The target is not short-term production. The target is long-term containment. That means we must protect the caprock, control pressure buildup, and avoid reactivating faults. Another important point is public confidence. If people hear that CO2 storage may trigger earthquakes, they may worry. That is why clear risk communication and strong monitoring are essential. CCS can be safe, but it must be designed carefully. Let us simplify the CCS risk pathway. The CCS risk pathway can be explained in 4 steps. Step 1. CO2 is injected into a deep reservoir. Step 2. Pressure builds around the injection well. Step 3. The pressure footprint expands through the formation. Step 4. If the pressure reaches a critically stressed fault, the fault may become less stable. This does not mean every CCS project will cause earthquakes. It means we need to understand the pressure pathway before and during operation. Now let us discuss safe CCS design. Safe CCS design starts with site selection. We prefer formations with good storage capacity, good injectivity, a reliable caprock, and low fault reactivation risk. During operation, injection pressure must be controlled. Engineers may limit injection rate, use multiple wells, or add pressure management strategies such as brine extraction. Monitoring is also essential. Pressure gauges, seismic monitoring, deformation measurements, and plume imaging can help detect early warning signals. The goal is simple: store CO2 effectively without pushing the system close to fault slip. Now let us move to underground hydrogen storage. Underground hydrogen storage is an exciting technology for future energy systems. Hydrogen can be stored underground when renewable energy production is high and withdrawn when energy demand increases. But UHS has a different pressure story from CCS. CCS is often long-term injection. UHS is cyclic. It involves repeated injection, storage, and withdrawal. Let us see this cycle visually. In underground hydrogen storage, hydrogen is injected into the reservoir. Then it is stored for a period of time. Later, it is withdrawn for energy use. This creates repeated pressure changes. Pressure rises during injection, remains high during storage, and decreases during withdrawal. If this cycle repeats many times, the rock and faults experience repeated loading and unloading. That is why UHS should be studied as a cyclic geomechanical problem, not just a simple storage problem. Why do these cycles matter? Cycles matter because the subsurface system is loaded, unloaded, and loaded again. Each injection period increases pressure. Each withdrawal period decreases pressure. This repeated change may affect well integrity, seal behavior, pressure communication, and fault stability. A single cycle may be safe, but repeated cycles over many years need careful evaluation. For non-specialists, we can compare this with repeatedly bending a material. One small movement may not matter, but repeated movement can reveal weaknesses. This leads to the key UHS risk question. For underground hydrogen storage, engineers need to answer several practical questions. How fast can we inject hydrogen? How much hydrogen can we withdraw? How large is the safe pressure window? Can repeated pressure cycling change that window over time? And how do we operate the storage system while protecting wells, caprock, and nearby faults? These questions show why UHS is not only a storage capacity problem, it is also an operational safety problem. Now let us compare the 3 systems side by side. Hydrocarbon production, CCS, and UHS all involve subsurface pressure change, but the pressure stories are different. In hydrocarbon production, pressure often declines. The reservoir may compact, and stress may redistribute. In CCS, pressure usually increases. The pressure footprint may reach faults before the CO2 plume does. In underground hydrogen storage, pressure rises and falls repeatedly because of injection and withdrawal cycles. The same basic physics connects all 3 systems. Pressure affects stress, and stress affects fault stability. Now the most important question: how do we reduce risk? Induced earthquake risk cannot be managed by guessing. It must be managed by measurement, simulation, and operational control. The goal is not to wait until a large event happens. The goal is to detect early warning signals and respond before the system becomes unsafe. This is where monitoring and traffic light systems become very useful. Let us look at the main risk reduction actions. There are 4 simple ideas for reducing risk. First, monitor pressure and microseismicity. Second, Use a traffic light system so that operation changes when risk increases. Third, slow down injection when pressure or seismicity becomes concerning. Fourth, use pressure relief strategies, such as brine production wells, to reduce pressure buildup near sensitive areas. The key message is, the best way to reduce induced earthquake risk is smart pressure management. But what exactly should we monitor? Different monitoring signals tell us different parts of the story. Pressure monitoring shows how the reservoir is being hydraulically loaded. Microseismic monitoring shows small slips or fractures that may occur before larger events. Surface deformation monitoring, such as NSAR or GPS, can show whether the ground is moving. Geochemical and well monitoring can also help detect unexpected leakage pathways. No single monitoring method is perfect. The strongest safety system combines several types of data. Now let us introduce the traffic light system. A traffic light system is a simple safety rule. Green means normal operation. The system is behaving as expected. Yellow means caution. The operator may reduce injection rate, increase monitoring, or review the model. Red means stop or take strong action. The risk is too high, and operation must change immediately. This system is useful because it connects monitoring data to real operational decisions. For the public, it is also easy to understand. Continue, slow down, or stop. Another strategy is pressure relief. Pressure relief means reducing risky pressure buildup. One method is brine extraction. If pressure becomes too high near an injection zone, engineers can extract formation water from another well. This creates more pressure space and can reduce the pressure footprint. Another strategy is to change the injection schedule, distribute injection across multiple wells, or redirect pressure away from sensitive faults. The goal is not only to inject more fluid. The goal is to keep the underground system within a safe operating window. Now let us see how simulation and digital twins help. Simulation is the bridge between underground physics and engineering decisions. We cannot directly see everything happening kilometers below the surface. But with simulation, we can create a virtual reservoir, test different scenarios, and estimate where pressure, plume, deformation, and fault risk may develop. A digital twin takes this one step further by updating the model with monitoring data. Let us look at the simulation workflow. A simulation workflow begins with a geological and fault model. Then we simulate pressure, fluid movement, and stress changes. Next, we evaluate fault stability using geomechanical indicators. Finally, we compare different operational strategies and choose safer options. For example, we can test several injection rates before the project starts. We can ask, which rate gives good storage performance while keeping pressure below the risk threshold? This is why simulation is so powerful. It allows us to test decisions before we apply them in the field. But simulation needs good data. Better data means clearer risk decisions. We need rock properties such as porosity, permeability, and compressibility. We need fault location, orientation, and mechanical properties. We need pressure data, wall data, and sometimes seismic or deformation data. We also need uncertainty ranges, because the underground system is never perfectly known. A strong study does not pretend that everything is certain. It asks, what happens if the fault is closer than expected? What happens if permeability is higher? What happens if pressure spreads faster? This is where AI and digital twins become exciting. AI can help accelerate subsurface decision-making. A physics-based simulator may take a long time to run many scenarios. AI models can learn patterns from simulation results and produce fast forecasts. This is useful for uncertainty analysis, optimization, and real-time monitoring. But AI should not replace physics. It should support physics. The best digital twin combines simulation, monitoring data, uncertainty analysis, and fast AI models to update risk forecasts continuously. Before we finish, let us discuss common mistakes. Beautiful animations are powerful, but they are not enough. One common mistake is showing only the plume and ignoring the pressure footprint. Another mistake is ignoring fault uncertainty. A third mistake is using a single deterministic model and pretending the result is certain. And a fourth mistake is giving the public a complicated explanation without a clear safety message. For induced earthquakes, communication must be simple, honest, and scientifically grounded. So what is the non-academic message? Here is the entire video in 4 simple sentences. Energy operations change pressure underground. Pressure changes stress. Stress changes fault stability. If we monitor and control pressure properly, we can reduce the risk. This is the message I want viewers to remember. Induced earthquakes are not magic. They are a physical response to pressure and stress changes in the earth. And because they follow physical rules, we can study them, simulate them, monitor them, and manage the risk. Let us finish with the final summary. Let us summarize. First, subsurface energy operations change pressure. Second, pressure changes stress on faults. Third, hydrocarbon production, CCS, and underground hydrogen storage all have different pressure stories. Fourth, earthquake risk depends strongly on fault conditions and pressure pathways. Fifth, monitoring, pressure management, simulation, and digital twins can help us operate more safely. So, can underground energy projects trigger earthquakes? Yes, under some conditions, they can. But with good science, good engineering, and good monitoring, we can understand the risk and reduce it. Thank you for watching. If you found this video useful, please like, subscribe, and comment with the next topic you want me to explain using dynamic reservoir simulation.